So tonight you have a problem on your homework that we did not cover in class. We did not do an example of it in class. And it requires defining one variable in terms of another variable when you have too many unknowns. Okay, this is a technique that we have not yet used. So I'm going to show it to you in this example here. Okay, so we have a conical tank vertex down, and it's 10 feet across the top and 12 feet deep. So what does that look like? It looks like an ice cream cone. Okay, and there's a faucet that is filling it. Maybe it's a hose or something. All right, and water's pouring in and filling it. Okay, and what we know is that the cone is 10 feet across. And I'm actually going to do this, because whenever I can, I try to define things in terms of triangle, because that's just kind of the way these things work. So it's 5 feet across because it's 5 feet of radius, even though we were given 10 feet of diameter. And the height of the whole thing is 12, and these are each feet. Okay? So let's catalog what we know. Okay? We know that the radius is 5. Okay? We know that the height is, I know that GDP is 10. Okay? And what we need, find the rate of the change of depth of the water. We call it D, or we could call it H. Because sorry. So what we need is we need the H. And the question is, when do we need the H? And we want the H equals. Okay? Outstanding. Maybe another thing that we know in this, we know that volume is H. Okay, so Tyler, so it might just become building. And if you okay, so usually what we would do is we would take the derivative of it, because we have ddt. We need dHdt. But here's the problem. We have D and R and N. After using the product rule to take the derivative of it, we're going to have a lot more variables than we don't have enough information to get rid of all these things. So we're looking for define R in terms of H. Find some way of expressing R in terms. And as a matter of fact, we do have a way of doing it because we have a relationship between the radius of this cone and the height of this cone. It's a proportion. So I'm going to do a little aside. I know the radius to the height of the cone 5 to 12. Since I want dHdt, the best thing to do is define this in terms of H. So let's solve this for R in terms of H. R is equal to 5H over 12. Let's now rewrite our equation in terms of h. So volume equals 1/3 pi times 5h over 12 squared h. So this is good because now we have an equation that involves only h and b. Well, before I start taking the derivative of this, I'm going to volume equals, I'm taking a couple, pi over 3 times 25h cubed over 144. Okay, so let's just make sure we're all on the same page here. Where everything inside and h. So I'm going to try to consolidate here. I get 25 pi h cubed over 3 times 144, which is 432. So 432. Okay, that's kind of ugly. All right, so now we can take the derivative of this, and we get dv dt equals 25 pi over 432 times 3 times h squared dh dt. Okay, and I'm going to end up dividing this thing by 3 again, which I multiplied it out, which I knew that was going to happen, but we had to see it. So therefore, dv dt equals 25 pi h squared over 144 times dh dt. So let's take a little inventory. We are looking for this. We have the height. We have that. And we have this. We have that. It is 10 cubic feet per minute. We can plug all those things in. We have 10 equals 25 pi times h squared over 144 times dh dt. I'm going to need my calculator for this, not going to lie. So I get 8 squared times 25 pi. We're going to try to make this cooperate with me. Pi, enter, divided by 144. All right, let's see if that works. Okay, so now I have 34.91. I'm not going to get rid of that on my calculator. On this side, 34.91, 34.91 dH dt equals 10. I'm going to divide 10 by that. Okay, so I'm going to do, it's just not cooperating with me, but I'm going to do 10 divided by answer. Nope. Nope. Divided by answer. Enter. And there's my answer there. Let's grab you and put you out here.
So we get, what does that mean? So the height is increasing at a rate of 0.286 feet per second. Okay, if we go back to the problem here, we want to know how quickly the water is increasing. Oh, and I'm sorry, it's not per second, it's per minute. Yeah, so it's per minute. Okay, and that seems reasonable. That seems reasonable. It should be slowing down as it gets up to the top because the surface area is getting larger, and so it's taking longer for the height to rise. And that makes complete and total sense. So there it is.